All right, welcome back. In this video today, we're going to discuss uniform circular motion. And if you've taken classical physics at the basic level, you've certainly learned the formula for the acceleration, which is known as the centripetal acceleration, which is known as the speed squared divided by the radius. And what I want to do today in this video is to derive this formula, but in a more careful way so that you can see not only how to use this formula, but first and foremost, how it is derived, why the formula has this expression, and even more importantly, why the acceleration in uniform circular motion always points radially inward towards the center. So let's start here with the circle that I have here on the left. And let's imagine that that's a track. And let's say that there is a person who is running counterclockwise around this circle, and he or she is running with a constant speed v. So at that point, the person is right there. That didn't work, so let me do it again. Right there, and the velocity of the person is tangential to the direction of motion. Now clearly, the circle will have a radius. So let's call that radius there, r. And the first thing that we notice is that the radius makes a 90-degree angle with the velocity. Now this is true at every point in the circle because as the person, say, runs counterclockwise, the radius will change accordingly. So after a certain time, the radius will be this one here. And clearly the length of the radius will be the same because the radius does not change in a circle. So if this one is r, the second one is r as well. And the person will have gone an angle theta between the two radii. And the velocity, as a result of that, because we're talking about uniform circular motion where the speed is constant, the only effect of this on the velocity is to change its direction but not the magnitude. So we can draw the same vector as the green one, but here, like that. There. So the length might not be the same because of the way I drew it, but you guys get the idea. And therefore, this is also v. So now let's talk about the displacement of this person. The displacement that has been taken by this person is the difference in position from this initial point here to this final point there. So we could draw a straight line that connects the two, and that will be our displacement. However, the actual distance traveled by the person is the distance along the blue arc that connects the initial and the final point, namely the blue arc that encloses the displacement line. Now, those two are clearly not the same, but generally we can consider an infinitesimally small angle, or in other words, we could consider an angle right here, and therefore in that case, the blue arc is almost the same as the black line segment. So in that case, the distance and the displacement line are roughly the same. And because generally in physics, we look at infinitesimal quantities, we can make this approximation and we're gonna call this distance along the arc delta S, and this displacement here, d, we're just looking at their magnitudes. That's why I'm not putting the vectors there. And so we can say that delta S is approximately d for small angles. Because at the end, we're going to look at the small angle limit. Okay, so now these are the two approximations. Now, as I said earlier, we also know that the angle between v and r is always the same. Now, in the process of going from the initial to the final point, we have gone an angle theta counterclockwise along the circle, which means that the radius has swept an angle theta. But because the velocity always makes a 90-degree angle with the radius, that means that the velocity vector also had to rotate by the same angle, theta, with respect to its initial orientation. So that means that the angle between the initial and the final velocity is also theta. Now, why do we care about this? Because with this, we can now draw two similar triangles, namely two triangles that share the same angle, and they are the same, either isosceles or any other type of triangle. So let's see what I mean here. I'm going to take the triangle formed by the two radii in D, and I'm going to draw it here on the side. And instead of using D, I'm going to use delta S because of the approximation that we made up here. So here I go. I draw the triangles here. I really didn't need to draw that arrow there, but let's keep it. So this is the first triangle. So let's label things here. We have R, R, and as I said, we're going to call this delta S. And the angle between the two radii is theta. But because of what I just said, the two velocity vectors, which I have drawn up here, also make a triangle if I connect them like that. So we can draw the same triangle here for the velocity vector. Now I can say something. I can say this is V, because I'm looking only at the magnitude of the velocities, and the angle between the two is theta. So what is this thing here? Well, that is how much the velocity has changed. So we can call that delta V. So we have these two triangles now, and because they're similar triangles, we can compare the ratios of the sides within the two triangles. So we obtain, for the first one, that the ratio of delta S over R must be equal to the ratio of delta V over V on the other side. And the reason for that is because they share the same angle and they have two equal sides, so they're both two similar isosceles triangles. Now, how is this formula going to help me in finding the acceleration? Now, recall that the general formula for the acceleration is that the magnitude of the acceleration is given by delta V over delta T. The delta V here appears in this equation, so I'm going to solve for it by multiplying both sides by V and then rearranging my equation so that I get delta V is equal to V over R times delta S. Now, this is a physical situation. So if we think of this as motion from point 1 to point 2, that means that if I started at this point here and I ended up at this point, I must have done it in an interval of time. Namely, this would be the time t initial where I start and I end up here at some time t final. And therefore, the total time interval to go from point 1 to point 2 has to be delta t. This delta t is the time that it took to go from the first position with the horizontal radius to the second position with the almost vertical radius. And it's also the same time it took for the velocity to go from being completely vertical to tilted. So I can divide both sides by delta t to obtain the following. Now, the expression on the left here is just A, because it's whatever I just defined up here. The expression on the right is V over R multiplied by delta S over delta T. Now delta S is the distance traveled. So the distance traveled here divided by the time, it's nothing but the speed. So this is V over R times R, which is V squared over R. Okay, so now we've finally obtained at least the expression for the magnitude of the centripetal acceleration, which is the acceleration that causes the velocity in uniform circular motion to change just its direction, but not its magnitude. All right, so now we have this. The next thing we want to do is to find the direction of motion. And for that, we have to do a little bit of work with the vectors themselves. So I'm going to delete some of the things here in the circle that we don't need at the moment. So now that I've drawn these vectors here, let me label them again for you. So we have the two radii here, and the angle is still theta. And the two velocity vectors, now I'm going to label them as V initial and V final. And as I said earlier, I'm not a computer, so you shouldn't expect me to draw these vectors absolutely precisely in length because I'm doing it by hand. So I'll try to do my best. Now we want to calculate delta V, the vector delta V, which is V final minus V initial. So think of what this means. Recall from subtraction of vectors that if we want to subtract a vector from another one, we take the first vector, the one that we want to subtract, and place it tail to head with the other vector. What this means is that we have to take V initial in this case, as I've done here. We take this vector here, and we bring it all the way here at the tip of V final and flip its direction to subtract it so that we have V final plus negative V initial. So essentially, subtracting two vectors is the same as adding the first with the negative of the second. Okay? Geometrically, that's what it means. Now, delta V, which is the change of the two, is the vector that points from the tail of the first vector to the tip of the second vector. So in our case here, is this vector here. That vector there is my delta V. So why do we care about the direction of delta V? Well, because if I write this equation here in vector form, and I say that A is equal to delta V over delta T, I have a vector equation. A is a vector on the left, and on the right, the vectorial part of the change of velocity over time comes from delta V because delta T is a scalar, is a constant. What that tells me is that delta V and A are proportional to one another, and therefore A must always point in the same direction as delta V. Now, I've seen from this picture here that the direction of delta V is tangent to the circumference. It makes a 90-degree angle with the circumference. It's radially inward, it's parallel to the radius, and therefore it points towards the center. Now, I've done this argument at this point here, but I could have done it at any other arbitrary point on the circle, and I would still have obtained the same expression for it, because clearly this circle is a highly symmetric geometrical object, and therefore it doesn't matter at which point we apply this argument. So now we have both ingredients. We know from this expression here that the expression for the magnitude of the centripetal acceleration is always equal to V squared over R, as we claimed at the beginning. And this geometric argument here also shows that AC always points radially inward, or in other words, towards the center. Okay, So this is the full derivation. I hope you guys found it useful. Let me know what you think in the comments below, and I'll see you in the next video.